Thank you for joining us today. I'm Claudia Reuter. I'm director of the Roberts Innovation Fund, and we're very, very excited to be able to have each one of our awardees come up momentarily to share what they're working on. But our moderator today is actually Allison Malloy, who is a managing director with Connecticut Innovations, and she's going to come up in just a second, tell you a little bit more about her work, and start to introduce our awardees. So stay tuned. Allison?
Hi, everyone. Thank you. I'm Allison Malloy. Good to see you. I'm with Connecticut Innovations. Just a quick show of hands. How many folks have heard of Connecticut Innovations? Okay, great. So, I feel like almost everybody here. So then I'll just be really quickly. And is there anybody else here from CI right now? Okay, great. I'm just representing. So 2 seconds on CI. It sounds like most people already know about it, but there were some questions in the last audience. This was a great panel for whoever was here. They did such a terrific job about their emerging technologies and investing and so forth. But there was a question, why Connecticut? We're not going to get into it. We all pretty much know Connecticut's fabulous. But if anybody wants to talk about Connecticut later, feel free to grab me. And if anybody doesn't know about Connecticut Innovations, we are Connecticut's leading venture capital arm here in the state. We have about $500 million of assets under management, and we invest approximately $50 million each and every single year into early stage tech startups. We're one of the sponsors of the event. This is a fabulous event. And we're pretty much split between almost all the sectors that are presenting. So from climate tech to bioscience to technology, all other. And there were a few stats that I just have to throw out that I thought were interesting at the end of the last panel for anybody that was here, that was talking about dollars that go to either overlooked or underrepresented and female and diverse founders. And so for anybody who doesn't know, Connecticut Innovations launched a new fund last year. Well, two. One is the Climate Tech Fund, and the other one is the Future Fund. And so I spearhead our Future Fund. And the Future Fund is a $50 million fund that is focused on female and diverse founders. So trying to get more dollars into more people's hands. So we're excited about that. So with no further ado, I'm excited to be back here for the second time because I was here last year also. I think this is an amazing opportunity where the faculty and the students that work with the faculty are have an opportunity to get funding and kind of spin their ideas out from lab to market. So I'm going to read the quick paragraph so we all hear exactly what it is instead of my interpretation. But so the Roberts Innovation Fund is a lab to market accelerator fund designed to identify and support projects emanating from the Yale School of Engineering and Applied Science. The fund was made possible by a gift from Will Roberts, class of 1990. Awardees this year received cash amounts ranging from $85,000 to $135,000, as well as industry perks in the form of cloud computing credits and support from Microsoft, Amazon, and Google. So thanks to all that money, right? And we have 10 award recipients that we're getting an opportunity to hear from, either the faculty or the students that are helping them spin this great technology out. So the first person who we're going to put on the spot is James Liccato. Now, James, he's like the one that we only got we have a little line here. So I'm just going to say he's scaling catalytic membranes for oil and gas produced water treatment, industrial wastewater treatment, and reuse. Most of the other ones we only have names. But with that, James, please come on up. I think you have, 5 minutes, 3 minutes?
5. I think 5.
Q&A, no Q&A?
It's fine. Hopefully no Q&A.
That's it, 5 minutes and you're up.
Perfect. All right. Hello, everyone. Any song? Hello. Hello. There we go. Perfect. All right. Hello, everyone. I'm James Liccato. I'm a rising senior in Yale College studying chemical engineering, and I'm one of the team members in Professor Jae-Hong Kim's group at the Roberts Fund Awardee. I'm also here with my fellow team member, PhD student Claire Chenard in the back. And our project focuses on scaling catalytic membranes for oil and gas produced water treatment. So let's break down what this problem is. So in America, every barrel of oil that's produced comes with about 5 barrels of incredibly contaminated water, right? So this water, or produced water, as it's called, contains toxic contaminants, organic contaminants, heavy metals, and can have salinities up to 4 times that of seawater. To give you a sense of scale of this problem, last year over 1 trillion gallons was produced domestically of produced water, which is on the same order of magnitude as the entire water withdrawals from the Colorado River Basin. So it's a lot of water. So where does this water go? Well, again, if not treated properly, it goes into our groundwater, it goes into our oceans, rivers, into our waterways. And currently, offshore oil and gas platforms fail to treat this water adequately, right? So as wells transition, as they age, that share of water that they're generating increases, right? And so currently they use solutions such as granular activated carbon, or GAC, to trap and separate these contaminants from water. But GAC suffers from 3 major pain points that we were looking to address with our research and with this project in particular. The first is that GAC fails to treat small organics, so some of these things like organic acid, acetic, propionic acid, they flow right through. The second is that GAC is an incredibly wasteful life cycle, so especially offshore where you have to boat in and out waste is very, very expensive, and it has to be treated thermally, which is incredibly carbon intensive. And the third is that it's very costly for these platforms if they fail. These regulatory standards, they can be shut down for days or weeks, which can cost them a lot of money and endangers our environment. So that's the business case behind why we were trying to advance this research. And again, we're looking to replace this system, this failing system. So what does our solution look like? Well, our solution comes in the form of a membrane, and it's built upon years of research from our lab, where we focus on catalysis for advanced oxidation processes, which are basically just processes that can destroy aquatic pollutants. And that's exactly what our membrane does. The IP, the meat of this project is this catalyst that we've embedded in this membrane that generates reactive radical species from simple precursor salts. These radicals then attack and destroy the bonds in organic molecules and reduce them down to harmless products. And actually, this is why we've incorporated a company to target this market opportunity, right? So this industry, the oil and gas industry, is under intense regulatory pressure and will only be under more regulatory pressure as we approach the energy transition. And so currently the offshore market is around $18 billion. And so we went through the national I-Corps program last summer to do a lot of market discovery on this, talk with many offshore professionals, and identified a beachhead market for us of around $500 million in the US Gulf of Mexico. So what makes our technology better? Well, compared to GAC, which is a separative technology, Catalytic functions as a destructive one, right? And that's why it requires 1,000 times less energy to function and to achieve the same performance, because again, we're eliminating that secondary treatment step. We're just destroying these contaminants in situ. So currently, it costs around $10 per barrel of produced water to treat with GAC. But our projected OPEX is less than 50 cents per barrel, and this is mainly for the cost of those precursor chemicals. So again, our go-to-market plans, we're thinking about being a membrane manufacturer, and then again, working with OEMs to produce these skids, and then working with oil field service providers to pilot, integrate, and deliver these solutions to offshore platforms. But this technology is a platform technology, right? It can be applied across many different sectors that have problems with organic contaminants. So things like onshore oil and gas, specialty chemicals, food and beverage, and more. And so we really think that this technology and the technology that the Roberts Fund is funding really could be a breakthrough, especially in the water technology sector. And for us, the Roberts Fund bridges this critical technical gap between a proof of concept, which is that bench scale validation that we've showed, and a pilot. And the Roberts Fund fits right in there to help us build that prototype, allows us to fund a materials scientist to help us with scaling of synthesis methods, and also to achieve some of our other objectives up there. And again, the Catalytic team is equipped to build this with the Roberts Fund. We really could not do it without the Roberts Fund. We're very excited of the work that we're going to accomplish over the next couple months, and excited for all the support that we're going to receive. And ultimately, Catalytic's goal, as a research concept as a company, is to revolutionize membrane treatment in a water-scarce world. And so we know that the Roberts Fund will be a great tool in helping us achieve that. So thank you.
Thanks, James.
Thank you.
Looking forward to watching your progress as you graduate and move on. CEO, did you see that? Did you see his title up there? That's like big time. All right, next person is David Van Dyke, AI in your pocket. So excited to listen to this.
Thank you. All right. Perfect. Okay, hello everyone. So today I'm excited to present Azar AI. My name is David Van Dyke and I'm an assistant professor here at Yale in computer science and in medicine. And I'm here to share the innovative work we're doing at Azar AI. And joining me in this venture are my co-founders, Amin Karbasi, who's an associate professor in electrical engineering and computer science. And, sorry, hold on one second. Change the screen here. Also at Yale, and Amir Zandia, who is a machine learning research scientist. Our focus at Azar AI is on optimizing large AI models for speed and efficiency. So AI had a breakthrough moment in 2022, primarily driven by large AI models with billions to trillions of parameters, such as ChatGPT. And despite the breakthroughs we've seen in AI, this progress comes with substantial challenges. Firstly, there's a scarcity of necessary hardware for compute, with projected 5-fold increase in compute requirements just from integrating large language models into search engines. Secondly, the energy consumption of these models is massive. For instance, ChatGPT consumes 25 times more energy than Google, raising serious environmental concerns. And lastly, significant privacy concerns arise due to the vast amount of data required for AI training and operation. This increases the risk of data breaches and misuse. So addressing these challenges is crucial for sustainable and secure advancement of AI technologies. So to recap, the main issues include massive GPU or TPU clusters, significant environmental and sustainability concerns, and the need to share data and models with cloud providers. So we present an open source end-to-end pipeline to build and optimize efficient, high-performing, and secure LLMs for both enterprise and consumer-facing applications. Our solution leverages cutting-edge technology to optimize LLM efficiency at both training and inference. Customers can come to us at any stage of model development, and our optimization toolkit ensures a more efficient model for their task. Our advanced compression techniques reduce model size without compromising performance, enabling efficient storage and transmission. We offer software tools that optimize computational efficiency, allowing faster training, faster fine-tuning, and inference of LLMs. Enhanced privacy is ensured by enabling in-house AI model development, eliminating the need to share sensitive data with third-party cloud providers. We are world experts in optimizing LLMs, generative AI, and other AI foundation models. Our end-to-end toolkit integrates the most cutting-edge AI optimization techniques, including long context attention, model compression, memory reduction, and workload optimization. Our recently published hyperattention can yield up to a 270-fold speed up in practical applications. Adobe has recently implemented a naive version of hyperattention, already achieving a 20% speed up in their large-scale applications. With our expertise, we can achieve much larger optimizations. Google's Vice President of Research has acknowledged that hyperattention is making a significant impact at Google today, being added to their internal testing code base and used by several teams. Industry leaders like NVIDIA also have recognized the potential of the solutions focusing on LLM optimization. NVIDIA released TensorRT Model Optimizer, a tool that accelerates generative AI models' inference performance and integrates with the popular Hugging Face Transformers library. There has been rapid growth in machine learning development activities over the past 10 years. Driven by popular open source frameworks like Hugging Face and PyTorch, we expect this trend to continue with the mass adoption of generative AI applications. And this ongoing expansion provides significant opportunities for Azar AI to make a substantial impact by offering efficient and optimized AI solutions that cater to the evolving needs of the industry. From a VC funding perspective, generative AI and AI development platforms are experiencing the highest levels of transaction activity. This is evident in both the value of equity funding and the number of deals being made. This trend indicates significant opportunities for fundraising, positioning Azar AI to attract investment and accelerate our growth in this dynamic market. Our AI optimization technology is highly beneficial for several key industries, such as cloud providers, financial services, healthcare, and autonomous vehicles. These sectors are ideal customers for our AI efficiency solutions, showcasing the broad impact and versatility of our technology. Our team brings together a wealth of expertise and experience to drive Azar AI's success. In our core team, we have Professor Amin Kerbasi, Dr. Amir Zandia, and me, and we bring a strong background in machine learning, AI, and efficiency optimization. Our scientific advisory board comprises of Professor Daniel Spielman and Nicholas Christakis, who provide invaluable guidance and insights drawing from their extensive research and industry experience. Thank you.
Thanks, David. Did you guys see how many customers and sectors that they're going to be able to help and affect? That's a lot of different industries. It's going to be awesome. So I did want to take a second. Wait, he disappeared. I wanted to take a second to say, well, if he comes back into the room or if he just sat down, that this is also thank you to Dean Brock for helping with the with this program. So I think he scooched out, so now I just called him out. Sorry, Dean Brock. All right, well, moving on. Scott Shapiro, you're next with Leibniz AI.
Hi, thank you very much. Great. So I'm Scott Shapiro from Leibniz AI, and I'd like to talk today about large language models and formal methods for legal reasoning. Let me begin with the crisis of legal services in the United States. Low-income households simply cannot afford legal services, and as a result, have to go without basic essentials such as food, heat, and electricity. This is not just a problem for the poor, but also for businesses. In the United States, companies spend double, almost triple the amount on legal services than their global counterparts. The traditional way of solving legal problems, of course, is using human lawyers. The upside of human lawyers is that they're reliable and transparent-ish. The downside is that they're expensive. Recently, companies, of course, have been experimenting with AI-based solutions, which are cheaper, but have the downside of being unreliable and opaque. So what we need is reliable, transparent, and affordable solutions. Now, in order to develop effective and affordable solutions to access to legal services, you need two kinds of expertise. You need technical and legal. And that's where we come in. So my co-founder, Ružika Piskač, is a professor of computer science at Yale Engineering, and she specializes in program verification and automated reasoning. And I'm a professor at the law school here, and I'm a legal philosopher, and I specialize in the logic of legal reasoning. Together, we have won numerous industry awards, federal grants. We've published in top research venues, and we've even taught classes together here at the university. Let me show you what we've come up with. Something, reliable legal chatbots, what we call law bots. So imagine, and this is just a basic use case, you can imagine literally anything with rules this being used for. But let's say you get a letter from the city of Portland saying, you got to cut down your tree, it's too tall. So maybe you go to the City of Portland zoning website, and there's a bot, and you say, I live on Worcester Street, the city tells me I have to cut down my tree, it's too high, it's 53 feet tall, do I have to do it? The bot validates your information, you say, yes, that's in fact correct, and the bot then says, no, you don't have to cut down your tree because you happen to live in the Portland Aircraft Overlay Zone, which is a real thing, by the way, and the vegetation height is 75 feet, which is also a real thing, and it gives you the code section. And as I said, this could apply to any type of use case where there are rules. How do we ensure reliability? Well, right here is the user interface that we just saw, but behind the scenes what happens is that the user prompt gets translated via a specialized LLM into first-order logic or an appropriate mathematical formalism, and that translation is then validated. Meanwhile, the code will have been translated in a pre-processed form to first-order logic as well with formal validation. Then both of those sets of formula get piped to an automated solver, which is extremely reliable tools for solving logic problems. There, the formula are combined, the solver answers the question, spits out a technical response, which of course nobody will be able to understand, but that technical answer gets piped to another LLM that has been trained to speak like a lawyer to a client, in this case on zoning, giving a natural language solution. Now, the key thing here is that LLMs are being used in translation and explanation, but not in reasoning. In reasoning, we're using automated solvers, which are extremely reliable and fully transparent, so we can tell you exactly why you got the answer you got. In comparison, none of the competitors use verification, so therefore they cannot ensure reliability, nor can they ensure transparency. Legal services market is growing, is very large and is growing, but in some sense, the legal services market is a small part of this picture, really, because we're going after any type of market that's got a lot of rules, which is literally everything these days. We are partnering right now with Amazon and Yale Law School and exploring other use cases as well. So in conclusion, obviously legal texts are hard to understand. Our tool empowers people to understand how the law affects them, try to democratize legal reasoning. Oliver Wendell Holmes famously said, the life of the law has not been logic, it's been experience. We say the life of the law is logic, always has been, always will be. Thank you.
Thanks, Scott. That's awesome. I want to be like an early beta user, and then I want to plug my answers to always be no for anything that anybody asks me. What about this? No, no, no. Okay, no, it's always going to be yes. Congrats on that. So, okay, moving on. We have a double team that's coming up to present. So this is going to be so fun. So we have Lydia Watt and we have Ochi Durak talking about advanced novel PFAS treatment technologies from lab to commercialization. I actually did need to look up what that acronym meant, but so maybe you can talk to everybody about it. I found it on my own, but here, how do you guys want to do your? Oh, gotcha.
We have another one.
Fantastic. Thank you.
Okay.
Good afternoon, everyone. My name is Lydia Watt, and I'm a second-year PhD student in Professor John Fortner's lab in the Department of Chemical and Environmental Engineering.
Hi, everyone. My name is Durak. I am also a second-year PhD student in Fortner lab, and today we are going to introduce what we do in lab, and basically to fight with PFAS and advancing novel PFAS treatment technologies for commercial usage. I would like to start to mention why this technology is important and has an urgency to us in immediate future because PFAS are pervasive, toxic, and must be urgently addressed. They pose a significant global health threat due to their really stable nature. They don't degrade by themselves in nature, so we need to have new technologies to fight with these components. They are really big health threats for numerous of illnesses such as cancer-related diseases, thyroid diseases, and many other diseases. U.S. spends upwards of $60 billion annually on PFAS-related health issues, and this number is around $50 billion for Europe side of the world. They are also known as forever chemicals because they are everywhere, and they are including our drinking water, which is very, very important. They are side products of many industries such as firefighting foams, retardants, pesticides, herbicides, paints, and also packaging. As in this map, you can see the current PFAS contamination of U.S. In U.S. alone, it's overly estimated around 57,000 contaminated sites, and we are getting affected by this contamination individually every single day.
As we've shown in the previous slides, the scale of the impact of PFAS on the human population can't be understated and will impact the treatment market for decades to come. So in April of this year, the EPA finally set enforceable drinking water concentration limits of 4 parts per trillion for PFOA and PFOS. These are the 2 most common PFAS compounds found in nature, and this will leave tap water for over 100 million people out of compliance. Currently in the US, it's estimated between 18 and 80 million people have tap water with at least 10 parts per trillion PFOA and PFOS. That's over twice the EPA limit. And over 200 million people have tap water with at least 1 part per trillion PFOA and PFOS. Due to the highly stable chemical nature of PFAS and the low concentrations needed to be reached, conventional water treatment technologies are inexpensive and inefficient for removing PFAS. Just to expand on this, material costs for production of PFAS range between $50 and $1,000 per pound. But removing PFAS from municipal wastewater, for example, costs between $1 million and $10 million per pound. If we're looking at drinking water costs, just to meet EPA regulations, we need to spend almost $50 billion in treatment infrastructure and $5.3 billion annually in operational costs. And to further talk about environmental remediation, if we just take Department of Defense cleanup sites alone, it is estimated that $31 billion is needed with only $2 billion committed.
To measure PFAS at low concentration, we need very specific and special equipment, which we have in our lab, 2 of these equipment, namely liquid chromatography coupled with high-resolution mass spectrometers. And in the Fortner lab, we combine world-class experts. As on this slide, as you can see, Lydia and I are here, and the other lab mates are working in the lab. And our group is led by Professor John Fortner, and we are in the process of developing new novel technologies. Currently, we have 4 novel breakthroughs in PFAS treatment technologies.
So I'll talk about 2 removal technologies that we have in lab. The first is a novel magnetic nanomaterial with a specialized surface coating designed to pull PFAS out of water. This can achieve up to 100 times more PFAS removal than standard sorption technologies. It's regenerative, cost-effective, and easily removed from water. Additionally, we have a completely green chemistry-based pathway to immobilize PFAS, which requires the addition of an environmentally friendly, cheap chemical and a very low energy input. So this is an exceptionally low cost, and both of these have patents filed for them.
As another novel approach, we are working on photocatalytic driven degradation pathways to defluorinate or destroy PFAS via sunlight or UV radiation. This reaction requires only UV radiation or sunlight and has exceptionally low cost. And as another novel approach, we are working on electrochemical-based processes to quickly destroy PFAS. These processes are rapid, durable, and has very high process stability. Both of these technologies are in the progress of getting a patent application.
So our next steps are to pave the way towards commercialization by doing performance evaluation with real-world samples. So we're very grateful to have the Roberts funding to be able to test our technologies with over 20 contaminated waters from a variety of sources. And then we'll proceed with performance evaluation and things like technology stability, techno-economic analysis, and life cycle assessments. But we're very excited to see the market viability and further the global impact of the technologies that the two of us and our colleagues work on every day in lab. And with that, we'd like to thank you so much for having us.
Thank you.
Nicely done, ladies, nicely done. Right, sometimes it's hard for two people to do a pitch. They pulled that off very well. Okay, the next person is Rebecca Livonian. So Rebecca, we're going to talk about towards manufacturable shortwave infrared vertical cavity surface emitting lasers. I mean, so smart, right? I'm so excited. Here you go. Getting smarter just being in this room.
Thank you. Yes, good afternoon. So my name is Rebecca Livonian. I am the CSO of Infrared, and we're really delighted to be a Roberts Innovation Awardee this year. So today we are at the fourth wave of human-computer interfacing, starting in 1970s with just text on screen, then graphic user interfaces, then smartphones, just touch screens. Now we are at spatial computing. I know many of you are probably familiar with the Vision Pro. You've heard about the Vision Pro. But even if not, you probably have heard of Internet of Things. You probably even have a smart device. You may or may not know that in all these smart devices, there's a tiny laser. Just like our human eye allows us to see and interact and understand the world around us, this tiny laser in the smart device allows it to identify objects and other smart devices in the world. We call this 3D sensing or imaging, and this is what allows digital components to blend with the physical world. The problem today is that most of these tiny lasers see in the wrong color. They usually see in visible light, or sometimes a little past that, what we call near infrared. But ideally, we want these lasers to see in what I call shortwave infrared, or SWIR wavelengths. SWIR wavelengths have three advantages. First, they're absorbed by the water in our eye, so they're eye safe, very important when we talk about lasers. Second, they have very low background noise. They see perfectly well whether it's rainy outside, sunny outside, foggy, or dark. That's really useful for these outdoor sensing environments. And third, they're compatible with the see-through glass used in most touchscreens and displays. This allows for more seamless blending of the digital and physical worlds. For the past 30 years, though, the optoelectronics industry has really wanted to make SWIR lasers, but they have not been able to due to fundamental challenges. I'll draw your attention to this cartoon block. This is a laser. The cone of light is coming out of the top of it, but then you can see these sandwich structures. These two form a mirror. To have an efficient laser, you need a very reflective mirror. And a good mirror requires high index contrast between the layers that make it up. Index contrast is a material property based on the atomic elemental properties of the material. It's difficult to change. But this is where Infrared came up with a eureka solution, so to speak, that's simple and scalable and ready for market. And I'll explain it very briefly with this cartoon. So in the block on the left, the blue and dark blue layers together, they form one mirror. These two shades of blue have low contrast. That's just a material property. But Infrared used an electrochemical process to selectively turn the dark blue layers into a sponge version, a porous version. Now suddenly the blue and white layers have very high contrast, and this becomes a very efficient mirror. We demonstrated and patented and proved this concept in a laboratory in a working SWIR laser in April 2023, so last year. I already mentioned that the industry has been trying to achieve SWIR lasers for 30 years. And so there are other competitors in the space, but primarily our competitors have fallen into two buckets. Either It is very difficult and therefore costly to grow the material, or it's difficult and costly to fabricate the material. However, our technology relies on a very mature foundry growth and simple wafer-level fabrication. So we provide the only low-cost and manufacturable solution on the market today. I mentioned that we proved our concept in 2023 of April of 2023. So in the past year, we've created significant traction with customers, industry partners, suppliers, and foundries, and VCs. With the rise of spatial computing, VCSELs are more important than ever. This is a very large market, and we are the team that's poised to capture this opportunity. So we are targeting immediately a $1 billion entry market of consumer and mobile VCSEL sensing, but you can see that there are several emergent growth horizons. We're very grateful to Roberts Fund and all of Yale Ventures for supporting us to reach our commercial targets, engage our customers, and increase our valuation. The Roberts Fund has gone to support the laboratory of Professor Jung Han at Yale, whose laboratory developed this technology. As I mentioned, I'm Rebecca. I lead business development for our company. We have a very lean team right now, only 4 people, but between our team, we have decades of experience, and we have a record of shipping and deep understanding of the problem space. We're really excited to be the team to commercialize SWIR VCSELs. Thank you very much.
Nice, Rebecca. Thank you. All right, moving on. We have 5 more to go. Today, Shin is going to be talking about a manufacturable process for a material to combine logic and memory in semiconductor devices. Oh, here you are. Here you go.
Thank you. Hi, I'm Kide from Yale Applied Physics, and this right here, this is my iPhone 14. It has 16 billion transistors in it, and just 50 years ago, the best computer chips only had 2,000 transistors. But we've been doubling the transistor count every 2 years, and we're close to 20 billion now. Now, this explosive growth in compute is arguably the main driver of innovation. But the problem is, how far can this go? Jensen Huang from NVIDIA says it's already over. And yes, we are in fact slowing down, mainly due to the fact that the chips are so dense now. We're putting more and more transistors into these computer chips that the computer chips are almost as hot as nuclear power plants. So this is power density, so that's power per area in the computer chips, and they're right below the nuclear reactor. And the implication of this is that to further scale aggressively, we really need innovation at the transistor level. We have to make the transistors themselves inherently and dramatically more energy efficient. And that's where the physics comes in. On the left is a conventional transistor. You have a silicon, and you have an oxide layer that's an insulator. So in this case, that's silicon dioxide. And to turn that thing on, you just apply power to the gate that creates voltage in the insulator, which in turn creates a bridge in the silicon. Now current can flow through the bridge, and the transistor is on. If you cut the power off, the voltage is gone, the bridge is gone, and the transistor is not operating. So this is, and if you think about it, is highly inefficient because it's like a switch. But if you turn it on, and if you want to keep it on, you have to put your hand at it. You can't take your hand off. So it's highly inefficient, but there's a simple, conceptually simple solution to this, which is just swapping out that silicon dioxide layer with something called ferroelectric. Ferroelectric is a special type of material that can sustain its own voltage. So in case of a ferroelectric transistor, we call that FEFAT. What happens is you just pulse the gate with some small, short pulse of power. Now the voltage is created in the ferroelectric. It's sustained even without external power, and the bridge is again constructed and current can flow. If you want to turn it off, you can just pulse it again with voltage of an opposite sign. So this is highly energy efficient. This is just how we imagine the switches. You turn it on, you just flick it on and off. But why don't we have this yet? Clearly, this is the natural way to go. Well, that's basically due to materials challenge. It's hard to find a suitable ferroelectric material because ferroelectricity has this tendency to just disappear when you make them very thin, very small. And that's where our Yale solution comes in. we found a new class of ferroelectric material that's only one atomic layer of zirconium dioxide. So it's very thin, so highly scalable, but surprisingly still ferroelectric. But more importantly, it's a simple material. It's just zirconium and oxygen. It's highly compatible with the commercial fabrication process. So finally, with this material, we believe that we can really realize energy efficient transistors. And this is a big deal because transistors, they go into every single semiconductor devices, CPU, GPU, memories, you name it. And so this innovation at the transistor level really has the potential to impact the entire market, which is currently about 600 billion, but it is expected to reach more than $1 trillion in just 6 years. The industry is aware of this, so we've been funded by these companies for the last 3 years. But luckily for us, we now have the Roberts Fund, so we can really pursue our own IP based on this material. So we're developing industrial scale process for this material, and we're also working on developing some prototype devices. And these will be stepping stones for eventual commercialization. So that is the story of how we want to transform the most replicated artifact in human history, which is the transistor. And I'm Ki-Dae Shin. My PhD thesis at Yale was on this project. And I'm working with Dr. Fred Walker, who is actually inventor of crystalline oxide on silicon devices, and Professor Charles Ahn, who's a pioneer in nanoscale ferroelectricity. Thank you.
Thank you. Next up, we have Fenian Zia talking about geometric deep sensing technology. Awesome. Thank you so much.
Sorry.
I can start it over.
Confused.
No worries.
Hello. Okay. Thank you. I'm going to talk about the new optical sensing technology we developed in our lab with our collaborators. So the title of my talk is called Cipher Light. We want to use new sciences we developed to decipher the properties of the light. Okay, so we're going to work on a very special wavelength range called mid-infrared, which spans from 3 micron, roughly from 3 micron to 15 micron, which is a so-called fingerprint of many different kinds of materials. Because the pattern of the absorptance peak in this range is unique for every different type of molecule. And this spectrum range has a lot of potential applications, ranging from real-time industrial process monitoring all the way to semiconductor manufacturing, and also many applications in research. Okay, so traditionally, if you want to look at the spectrum of certain of the light, usually what we do is we kind of spatially split the light, either based on its wavelengths or based on the polarization, and then detect them individually. And but this is very challenging in this very special spectrum range, due to both the detectors and also the light splitting components. So currently in this spectrum range, the community usually use very bulky and expensive instrument. The most popular one is called FTIR, Fourier Transform Infrared Spectrometer, which can, the price can go from like about $20,000 all the way to $150,000, so which are very bulky, and also usually requires liquid nitrogen cooling. And also it depends on the mechanical movement, and which is obviously very, very difficult and challenging to scale to small scale. But what the industry and the community want is something very compact, very inexpensive, and actually there are many government and industry efforts trying to bridge this gap. So what we came up with in my lab and with collaborators is two proprietary technologies which can address these challenging issues. The first is the detector in this mid-infrared spectrum range, and we discovered a new gain mechanism which allows us to do very sensitive mid-infrared detection based on traditional semiconductors. And second is a new technology we call geometric deep sensing technology, which combines the software and the hardware. So the main idea is that in traditional light detection, you have to split the light based on their wavelengths or polarization, then do the detection of individual component. But what we have done is we developed a holistic detection scheme in which we can detect all the information in a whole and encode them into a high-dimensional vector. Then we use a deep neural network to interpret this data, to uncover the information we want. So that gives us a lot of flexibility and greatly extend the capability of the detection scheme. So based on these two breakthrough technologies, so we are able to squeeze the, realize the functions which usually requires a huge instrument to something very, very tiny, to the, basically we're trying to build it on a chip. Okay, so compared with all existing technologies to do mid-infrared spectroscopy sensing, they either rely on very, very large interferometers, or they rely on bulky tunable lasers, or very complex frequency upconversion scheme. So our technology, we are going to rely on the light-matter interaction in the traditional classic semiconductor materials, plus a software, which is a deep neural network tailored to our hardware to realize all these functions. Okay, so this is our product roadmap in the mid-infrared. So the first thing we are going to do is we're going to develop, with Roberts funds, develop this high-sensitive, high-speed bolometer, and then we are going to do the single bolometer spectrometer. After that, after we lay out the foundation, eventually we are going to realize spectrum imaging and build the AI engine for the mid-infrared. Okay, so this is why I will skip this. So I will just use one user case to illustrate this concept. So for example, traditionally, you want to use the infrared signal to detect the skin disease. What you usually do is you cut a piece of your skin, okay? Then you do skin biopsy first, then you carry this small sample to a lab, then do the analysis. But with our technology, what we can do is we can analyze the light emission from your body based on the small spectroscopy array to directly analyze the condition of your skin. So this is the event. This is the timeline of our project. So we have already applied filed two patents. One is on the hardware, one is on the software. And this year, 2024, we already received the Roberts Fund. With that, we are going to move this project ahead, and we aim to demonstrate the prototype and both the bolometer and the spectrometer within 2-year time frame. Finally, I will briefly introduce our team. So the technology, both technologies are mainly developed by my lab and also my collaborator lab, Professor Malloy in University of Washington. And we have Ms. Tingley as leads the business development. And we also assembled an advisory board. And Dr. Wenliang Chen, he will advise us on how to bring the technology from the lab to the semiconductor manufacturing. And we have advisor from C1 Venture, Dr. Solomon Asafa, and we also have a physicist to help us address the fundamental physical issues in this project. Thank you.
I like that. Don't cut the skin. Don't cut the skin. I like that. All right. We're moving right along. Mark Saltzman, Evershield. Is that the name of your company?
It's the name of the project.
Okay. See, like, that's a nice short one. That's just Evershield.
Yes.
I like that.
Thank you.
I like that.
Thank you. So I'm done then. Well, thank you. It's a pleasure for me to be here to present about our project called EverShield. We focus on addressing the problem of long-acting drug delivery in situations where individuals need consistent daily drug treatments over long periods of time, and we do that by using an implant that completely disappears after the drug is administered. Here I describe more completely some of the needs for better long-acting drug delivery. A long-lasting, reliable implant will provide another alternative for people wanting long duration and convenient contraception that avoids surgery. For people living with HIV or at risk of acquiring HIV, the technology could provide reliable, long-lasting therapy in a simple format. We believe this technology also has the potential to lead to long-acting treatments for chronic conditions such as endometriosis, arthritis, and pain. Our solution is shown here in the tube. You see the technology. It's fully degradable polymer implants which slowly and reliably release agents over long periods of time, and you can see that in the graph on the slide. In the left, you see our polymer implants. They're produced from a novel polymer, which I'll describe in a minute. The implants, these particular ones, are 2.4 millimeters in diameter, and they can be manufactured in variable lengths, which controls the amount of drug that you're introducing with the implant. An experienced team has brought the project to this point, including myself and Seung at Yale, as well as an experienced group of partners at FHI 360, including Jennifer Ayers, Bruce Cow, and Greg Koff. With this team and many years of non-dilutive financial support, we've established the feasibility of our approach. We've issued patent with claims covering the novel polymer as well as elements of implant design. We've developed scalable methods of manufacturing. We've completed an integrated product development plan with clear milestones, and we now seek to demonstrate that these implants can provide long-acting, safe, and reliable treatment of HIV. To provide more detail on the progress, I show you the enzyme-mediated chemical reaction scheme we use to produce our unique degradable polymer. It's a polyester, a copolymer of pentadecylactone and dioxanone. We have tuned this reaction to laboratory scale and also transferred the technology to Polysciences to scale up the reaction to a batch size of 700 grams with good yield and retention of desired composition and molecular weight. With Lubrizol, we've developed a co-extrusion method for production of core sheath implants at scale, where the drug is contained in a degradable polymer sheath, and that's shown in the green on this diagram, on this microscopic image, that surrounds a fully degradable polymer core, that's the blue. This core sheath design allows us to control both the duration and the rate of agent release. These manufactured implants can be sterilized by gamma or E-beam irradiation with no change in polymer properties or implant release characteristics. When implanted subcutaneously in rats or mice, these implants are very well tolerated, with biocompatibility similar to other approved non-degradable implants. Importantly, despite releasing agents for many years, the implants are mechanically stable through much of their lifetime, so they can be removed if you want to end therapy early. This is our first preclinical example with a contraceptive levonorgestrel, and what I show you in the two graphs here is the daily release rate measured by just incubating the implants in water, and also the serum concentrations in an animal after they've received a single implant. And this gives reliable serum concentrations that match very closely the daily release rate over a period of almost a year and a half. This shows a second preclinical example where we used antiretroviral agents, and we've implanted them into humanized mice that were then infected with HIV. And you can see that this implant protects from viral load, reduces the viral load in the implants, and protects from the death of T cells. This slide compares our technology to existing products. There are other long-acting implants. It shows two axes here. One is degradability. It's either degradable or it's not degradable. Not degradable means it requires a surgical procedure to remove it, and duration of release. And while there are some short-acting degradables that work over 1 to 3 months, there's no long-acting degradable implants available for any of these indications, and that's where we have our opportunity. We're thinking here in this Roberts Fund project about further developing the anti-HIV treatment and developing prototypes that will then be ready for testing in large animals and eventually, we hope, in people. But we're also thinking about other applications because this is a platform technology. I talked about contraception. We think endometriosis is a real huge unmet need that chronically affects many women. And I've been astonished at what fraction of women suffer from endometriosis, and also could be useful for chronic pain like that of arthritis. So thanks again. Delighted to have the support of the Roberts Fund to be with this spectacular group of innovators at Yale, and I thank you.
So important. Important work everyone's doing here. Okay, Youngshan Ding, doing data-centric quantum computing. So take it away.
Thank you.
And then say your name again. Just
Youngshan. Yeah,
All
you
right,
did it well. All right. Thanks, everyone. I'm Youngshan Ding, Assistant Professor of Computer Science and Applied Physics here at Yale. It's my pleasure to be here and share the exciting project we have on data-centric quantum computing. For full disclosure, I'm also a consultant to Quantum Circuits, Inc., a quantum computing startup spun out of Yale Applied Physics, my colleague Rob Shukov's lab. I'd like to begin by saying that we enter the second quantum revolution, where we will harness the quantum mechanical properties of atoms to encode, to store, and process information. Well, the first revolution of quantum mechanics already brought us many amazing technologies such as lasers, MRIs, atomic clocks, etc. By understanding atomic behavior at nanoscale. But this time around, we want to build a quantum computer, which is promised to revolutionize the technology industry by bringing the so-called quantum speed-up to many data processing tasks. At its core, we're building this device called quantum bits, or qubits, whose superposition and interference properties allow us to process multiple data at the same time while using exponentially fewer resources than conventional computers. Here I highlight a few of the industry sectors that would experience the most impact by quantum computers in the near term. Advanced quantum algorithms has been developed over the last 3 decades. For example, short factorization algorithms has huge implication to data privacy and encryption. Quantum simulation algorithms can speed up drug discovery. Quantum optimization algorithms can improve efficiency of compute-intensive tasks in the logistics and energy sectors, and the list goes on. But to reach practical quantum computing, where large scale of data will be involved, we face a key challenge where what we call the quantum data I/O bottleneck, where the amount of time it takes to encode data into a quantum computer will be the dominant overhead of a computational task. And quantum random access memory, or QRAM for short, is the crucial technology for shorten this data access time and thus enable quantum computing at a more practical scale. So our unique approach to scaling is through developing advanced QRAM technologies. So on the left, the conventional approach to reach practical scale quantum computing is by building quantum processors with more qubits and better quality qubits. And yes, we're seeing steady improvement over the years, these dots representing different QPU, quantum processing unit prototypes from industry. They're moving slightly over to the right, top right corner of the figure, where you have increasing system size and increasing system fidelity. but there's still a huge gap between, there's still a huge gap to what the algorithm really need. And our approach is, we showed that to truly harness the power of, to truly harness quantum speedup, we need more balanced efforts to also advance quantum random access memory, where we build an architecture that multiple QPUs will talk to the QRAM unit in a shared architecture. And in our lab, we have built the most advanced QRAM architecture where it's outperformed the existing QRAM architectures in virtually all metrics, including compilation latencies, bandwidth, and fidelity, and so on. So we're fortunate enough to receive a Roberts Innovation Fund to further develop these ideas and improve the QRAM architecture, hardware architecture, and software architecture to really support quantum algorithm at scale with high speed and high fidelity. And in the next year, we plan to prototype our design, a QRAM design, onto actual quantum hardware platforms, such as the Quantinuum, a company building trapped ion quantum devices to benchmark our QRAM devices. And bring the new technologies from our lab, including the second-generation quantum routers and shared memory architecture and advanced software interface to actual quantum algorithm developers. Finally, I'd like to acknowledge and thank my team, which is the Quantum System Lab that I lead with my grad student Shifan Xi, and also collaborators at the Applied Physics Department, Professor Steve Gervin and Dr. Danny Weiss. Also external partners from across the country, and also our generous funders from Yale Engineering, the Roberts Fund, NSF, and YQI. Thank you.
So much. Last but not least, we have one final pitch, and Josh Beal, Crania, on decentralized machine learning as a service. So here we go.
Hi everyone, my name is Josh. Today I'll be presenting Crania, our ongoing research project on decentralized machine learning as a service. This work is done in collaboration with my advisor, Professor Ben Fish. So as we all know, AI is eating the world. It's becoming an increasingly important part of nearly every industry and everyday life. And as a result, the market for AI infrastructure is exploding. Machine learning as a service is a $70 billion industry today.